Today it's exponential and logarithmic models. So, the 5 most common types of mathematical models involved with exponential or logarithmic functions are listed below. Exponential growth, y equals a times e to the bx power where b is greater than 0. This is probably one that we'll use the most. Exponential decay, y equals a e to the negative bx where b is greater than 0 again. So the only difference is this is a negative exponent now it's exponential decay. The Gaussian model, y equals a times e to the negative x minus b squared divided by c power. Logistic growth, y equals a over 1 plus b e to the negative rx power. And logarithmic models, y equals a plus b natural log x, or y equals a plus b log base 10 of x. So we've got some graphs here, kind of show you what these look like. Here's your exponential growth, exponential decay, Gaussian models. Sometimes you hear the bell curve. There you go. Logistic growth. A lot of times this is used with things that have diminishing returns, natural log, and the common log. Okay. So example 1, the table shows estimates of the world population in millions from 2007 through 2013. An exponential growth model that approximates the data is p equals 6,128 e to the 0.0113 t power, where p is the population in millions and t equals 7 represents 2007. According to this model, when will the world population reach 7.6 billion? Okay, so let's see, this is all in millions, so 7.6 billion would be 7,600 millions. So we want to know when that's going to equal 6,128 e to the 0.0113 t power. All right, so our first step is we're going to divide both sides by 6,128. So 7,600 divided by 6,128, this is going to be 1.2402 equals e to the 0.0113 t power. Now, this is not exactly this number. I'm going to leave that number in my calculator. I'm going to use my answer key, which if you look at your graphing calculator down here at the negative sign at the very bottom, the answer key is right above that. You push the blue key and then the answer key, and it carries the entire answer forward. So the next thing I need to do is I need to natural log both sides of this, and that's going to get rid of the e. So I'm going to get 0.0113t is going to equal the natural log of 1.2402. And then I'm going to divide by 0.0113 on both sides. So t is going to equal all of this stuff right here. All right, so this is just a matter of doing it on my calculator now. So I'm going to take the natural log of my answer. Whoops, I hit the wrong key. Hang on. The natural log of my answer divided by 0.0113. And that comes out to t is approximately 19.05. Which, if t equals 7 represents 2007, then t equals 19 would be, the answer would be 2019. Okay, so, not too difficult. In a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies, and after 4 days, there are 300 flies. How many flies will there be after 5 days? Okay. So the first thing we want to do is we want to get down our formula. Okay, we're going to use our exponential formula. So let's see here. That's going to be y equals a times e to the bx. All right, that's the formula we're going to use. Now, what else do we have here? Well, we got a couple of points. We've got one point here that in 2 days I have 100 flies. So 2, 100. I've got another point right here for 4 days and 300 flies. And I got to figure out how many I'm going to have after 5 days. So the first thing I'm going to have to do is figure out, I got to figure out what these variables are going to be. Okay. So the first thing I'm going to do is I'm going to take these and plug them into the equation. So I'm going to get 100 equals a e to the 2b power. And then I'm going to plug them into the other equation. So over here I'm going to get 300 equals a e to the 4b power. Okay. Now, the problem is I still have two variables in each one of these equations. So what I'd really like to do is see if I can solve for one of those variables somehow and use that to plug into the other equation. So, I can easily solve for a right here. So a is going to equal 100 divided by e to the 2b power. I just divide by e to the 2b on both sides. So now what I'm going to do is I'm going to take this number here. I'm going to substitute it in here. Okay, so when I do that, I'm going to get 300 equals 100 e to the 2b times e to the 4b. Now, this e to the 2b in the denominator is going to cancel with the one in the numerator here. And I'm going to get, I'm going to subtract my exponents, so 4b minus 2b is 2b. And now I can divide by 100, so 3 is going to equal e to the 2b. I can natural log both sides. And I can divide by 2. So, I'm going to leave that exact value right there. I'm not going to change that into a decimal. So now I know what b is. So I can take that and I can put that back into my original equation. So, let's see, I can take that and put that up in here. So, let's see here, let's go 100 equals a e to the 2b, but b is the natural log of 3 divided by 2. And so now I got one variable, I can solve for a. So this is going to cancel. And then I'm going to get, this is going to be 100 equals a e to the natural log of 3. And then the e and the natural log cancel, so 100 equals 3a, and so a is 100 divided by 3. Okay, so now I've got an equation where I know a and b. So I get y equals a, which is 100 over 3, e to the b is 1/2 natural log of 3 times x power. All right, now I just got to know x, and I can solve my equation. So how many flies will there be after 5 days? I just plug in 5 for x. So y is going to be 100 over 3 e to the 1/2 natural log of 3 times 5 power. All right, so at this point I get out my handy-dandy TI-84 plus C Silver Edition graphing calculator. I put 100 divided by 3 in parentheses times e to the 0.5 times natural log of 3, close the parentheses, times 5 power. I hit enter and I get y is approximately 519.6, so we're just going to say 520 flies. And there we go. So that was a little bit tough work there, but it can be done. All right, the ratio of carbon-14 to carbon-12 in a newly discovered model is R equals 1 over 10 to the 13th power. Estimate the age of the fossil. Okay, and we know that R is 1 over 10 to the 12th power, e to the negative t divided by 8,223. Okay, so what we need to do is we're going to substitute this in for R. So I'm going to get 1 over 10 to the 13th power equals 1 over 10 to the 12th power, e to the negative t divided by 8,223. So to solve this, I'm going to go ahead and multiply both sides by 10 to the 12th power. That's going to cancel this, and I get e to the negative t divided by 8,223 equals 1 over 10. That's a little bit easier to work with. All right, I need to get rid of the e, so I'm going to natural log both sides. So if I natural log both sides, the e goes away. I'm going to have negative t over 8,223 is going to equal the natural log of 1/10. And then I'm going to go ahead and multiply both sides by, I'm going to multiply by negative 8,223. And that's going to get rid of the negative and the 8,223 over here. So negative 8,223, natural log of 1/10. And now it's just a calculator question. So here we go. Negative 8,223 times the natural log of 0.1. And t is approximately 18,934 and change. And that's would be in years. Okay. So a little carbon dating experience there for you. SAT scores. In 2013, the SAT math scores for college-bound seniors roughly followed the normal distribution of y equals 0.0034 e to the negative x minus 514 squared divided by 27,848, where x is between 200 and 800. and where x is the SAT score for mathematics. So use a graphing calculator to estimate the average SAT math score. Okay, so on this one I'm going to have to get out my calculator. I'm going to go ahead and hit y equals and clear out any equations that are in there. And then I'm going to put that equation in. So 0.0034 times e to the negative open parenthesis x minus 514, close the parentheses, squared, divided by 27,848. Okay, now my x's, so I'm going to have to go to my window key, and I need my x min to be 200 and my x max to be 800, and I'm probably going to count by like 50s on that, so my y scale, or my x scale is going to be 50. All right, then I need to figure out what my y's are going to be. Now these are going to be really tiny here, so I'm going to go from 0 to, I don't know, let's go 0 to 1 and see what happens. Count by 0.1, and I hit graph. And I don't really see anything happening. So let's go to table. And, okay, so if I look in the table, it shows me x's and y's, and the y's are very, very tiny. So I'm going to go back to my window, and I'm going to change my y max to be like 0.005. And we'll count by 0.001. And then I'll regraph it. Now I get a graph. Okay. So this is, actually I'm going to put this in here. This means that you skipped a whole bunch of stuff. Here's 200. Here's 800. Okay, this is 0. This is going to be 0.005, and my graph kind of looks like this. And this appears to be right around 0.003. So I'm supposed to find the maximum, or I'm supposed to find the average. So the average is going to be right here. So I'm going to go ahead and let's see. I'm going to find that where that maximum is. So I'm going to go second calculate maximum. Puts a little x right here. So I'm going to move the x over here. I'm going to left bound it. And then I'm going to move it over to the other side and right bound it over here. And then I'm going to have it calculate. And it tells me that this is actually 0.0034, but I don't really care what that is. I want to know what this is right here. And that comes out to be 513.99999. So we're going to count 514. And that's your average score. 514 right there. All right. So here's a logistic growth. Spread of a virus. On a college campus of 5,000 students, one student returns from vacation with a contagious flu virus. Wow, that doesn't have anything to do with right now, does it? The spread of the virus is modeled by this right here. 5,000 divided by 1 plus 4,999 e to the negative 0.8 t, where t is greater than 0. Where y is the total number of students infected after t days. The college will cancel classes when 40% or more of the students are infected. How many students are infected after 5 days? Okay, so that's pretty easy. T is 5. So I just go ahead and put in t equals 5. So y is 5,000 divided by 1 plus 4,999 e to the negative 0.8 times 5 power. All right, so this is a calculator question now. 5,000 divided by, in parentheses, 1 plus 4,999 times e to the negative 0.8 times 5 power. You got to arrow down and close your parentheses. All right, this comes out to be 54. 54 students. Oh, wait. How many students? Yeah, there you go. 54 students after 5 days. Now, after how many days will the college cancel classes? Okay, so if it's 40% of 5,000 students is 2,000. So on this one, we're going to know the y. Okay, so the y is going to be 2,000. And this time, we're going to solve for the t. So the first thing I would do is I would multiply this over to this side right here to get that off the bottom. So I don't like to have my variables in the bottom. So 2,000, 1 plus 4,999 e to the negative 0.8t equals 5,000. And now I'm going to divide by 2,000. So 1 plus 4,999 e to the negative 0.8t equals 5,000 divided by 2,000 is 2.5. And let's see, then I'm going to subtract 1 from both sides. And next I'm going to divide by 4,999. And then I'm going to take the natural log of both sides. So negative 0.8t is the natural log of this number. And then I'm going to divide by 0.8, negative 0.8. And we'll see what that is. So the natural log of 1.5 divided by 4,999, close the parentheses, divided by negative 0.8. T is approximately 10.1 days. Okay, so yeah, I closed up pretty quick. All right, magnitudes of earthquakes, logarithmic models. All right, so on a Richter scale, the magnitude R of an earthquake of intensity I is given by R equals the log base 10 of I divided by I sub 0, where I sub 0 is 1, is the minimum intensity used for comparison. So, like if you had a 10 earthquake, that is not 10 times bigger than a 1 earthquake. It's a lot, it's much, much bigger because it's a logarithmic scale. So, in 2014, Edgefield, South Carolina experienced an earthquake that measured 4.1 on the Richter scale. And in 2014, Nago, Japan experienced an earthquake that measured 6.5 on the Richter scale. Find the intensity of each earthquake. Okay, so what we're going to do here is we're going to take Naga, or we'll start with North Carolina. Okay, so R equals log base 10 of I divided by I naught. All right, that's our formula we're going to use. Okay, so the first one was 4.1 equals the log base 10 of I divided by 1. All right, so, and then I want to get rid of, so this is, I need to, this is I want to get rid of the log base 10, so I'm going to take 10 to both powers. So I is 10 to the 4.1 power, which is approximately 12,589. That's the intensity. Okay, now let's look at the one in Japan, which was 6.5. So we're going to do the same problem, except 6.5 is going to be over here, log base 10 of I. We don't really need to divide by 1 in this case. So 10 to the 6.5 power. Ten to the 6.5 power comes out to be 3,162,277.7. That is a lot more powerful than that. So if you compare the two intensities, you would just divide them. So divided by 12,589 comes out to be about 251.2 times more powerful. That's a lot. That's why you got this brand new high school here, because they were deathly afraid of an earthquake in that old building, and now this one's all built earthquake proof. As earthquake proof as you can be, I guess. Okay, so here we go. Here is our assignment. These are the problems that I would like you to do right here. There's not a whole lot of them. And there's the assignment. And again, I posted the problems, the homework assignments so that they're easier to read in Google Classroom. So I will see you later.